Assalamu alaikum and good morning. Today we're going to start with a new topic, which is going back to topic 5. This falls under physical chemistry. This will involve a bit of calculations and as well as theory and memorizing definitions. Okay. This topic is called the chemical energetics. Another name for this concept is thermodynamics. Okay, so often you will see that some textbooks and website will use the term thermodynamics. This means this is referring to the heat and the energy involved. Okay, so energetics will look at the enthalpy change, delta H. The first learning objective that we're going to look at is to understand that chemical reactions are accompanied by enthalpy changes, and these changes can be exothermic, delta H negative, or endothermic, delta H positive. Okay, so first we talk about energy transfer, because during in every reaction, there will be energy transfer from one system to another. Okay. Right, the definition of enthalpy change is the amount of heat energy either taken in or given out during any change in a system, provided that the pressure is constant. So in a reaction, depending on the type of reaction, whether it is exothermic or endothermic, there will be some energy in terms of heat that will be changing. Okay, so you all are familiar with the concepts of exothermic and endothermic, so I'm just going to go through this quickly. Exothermic are chemical reactions that release energy to the surroundings. So you would expect the temperature of whether we're talking about a beaker or a test tube or a solution of exothermic reactions to increase. It gets warmer. So sometimes when you do practical for qualitative analysis in question 3, you would notice that the test tube is getting warmer. That means it is an exothermic reaction. So whenever there's an increase in temperature, heat is being released into the surroundings, and that means it is an exothermic reaction. Endothermic reactions are chemical reactions that absorb energy from the surroundings. That means they take in heat for this reaction to occur. So you would expect the temperature of the surroundings to decrease. Not sure if you have come across this, but whenever you feel the test tube or a beaker or any of your household appliances, especially in aerosols, when you start, when the contents of your aerosols are at the last few quantity in the tin, and you would notice that the can would start to get colder. So this is an example of an endothermic reaction. Next learning objective is to construct and interpret a reaction pathway diagram in terms of the enthalpy change of the reaction and of the activation energy. Okay, so we want to look at the reaction pathway diagram, or sometimes called the enthalpy profile diagram. So an enthalpy profile diagrams will show you energy on the y-axis, and on the x-axis, usually they write it as progress of reaction. Okay, so you can see this as, say, maybe over time, okay, when we look at the progress of the reaction. So you can, an energy level diagram is a diagram that shows the energies of the reactants. So you can see the energy of the reactants and the energy of the products, okay, depending on the type of reaction. You will also see the transition state. Okay, so I'll talk about the transition state in the next slide. The transition state is something that you have come across when you've learned mechanisms in organic chemistry. So it is the temporary state before you get to your final product. Okay, and this is shown in the enthalpy profile diagrams. Okay, so if we look at the exothermic reaction, which is on the left, you start from the reactants having some amount of energy. Okay, and then as you go along, you notice that the energy is going up. Okay, so this is what we call an activation energy, right? In your notes, it says that the activation energy is the minimum amount of energy needed for the reactant molecules to have in order to start a reaction. Okay, so reactants need to overcome this minimum energy first. And once it once it has enough energy, then it can only turn into products. Okay, so my transition state is actually at the top here. Transition state. Okay, so the transition state is just a temporary state for the reactants to get to the products. So transition state will be gone once you have produced or formed the products. Okay, the activation energy is here. Okay, from the reactants up to the transition state, that's your activation energy. And then your enthalpy change, delta H, I forgot to mention in the previous slide just now, enthalpy change, the symbol is delta H, okay? Delta stands for change. The H is your enthalpy. Okay, so if you can just write down on your notes next to the definition of enthalpy change, okay, delta is change. The H is the enthalpy, is a symbol for enthalpy. During a reaction, we want to look at the enthalpy change, not just the enthalpy. Okay, so enthalpy, if you can imagine enthalpy as being the energy. Okay, so this is the energy of the reactants. It's at certain amount, and then the enthalpy or the energy of products is much lower than the energy of the reactants. Okay, so that is a characteristic of an exothermic reaction where the products have less energy than the reactants. You can see that the delta H, okay, from reactants, you're going down to the products. So that means your enthalpy change is decreasing. Yeah, your energy is decreasing. You start from a higher number, you go down to a low number. This is the reason why exothermic reaction has a negative sign. Okay, actually, you don't have to explain in terms of the enthalpy profile diagram, but I thought that I should let you know so that maybe it can help you remember better. Okay, so enthalpy change is a negative number and it is taken between the reactants and the products. Only this part. Okay, activation energy is from the reactants to the transition state, right? So don't get confused. Delta H is not from the transition state to the products. It would be the difference between the energy of the reactants and the energy of the products. You notice that the arrow is going up and the arrow is going down. Now, in this case, the direction of the arrow is important, okay? Going up means positive and going down, arrow down, means negative, okay? So just bear that in mind. Arrow down is negative, right? If you are used to drawing this double-headed arrow in O level, please stop doing that, okay? Because the arrow is a direction and it tells you the sign of your value of enthalpy. Moving on to the next, the energy profile of your endothermic reaction, okay? So again, your transition state is at the top here. Again, by definition of activation energy, it is the minimum energy required for the reactants to obtain in order for it to turn into products. Okay, so this is the energy of your products, which is missing, I believe, in your diagram, right? And you can see that the energy of the reactants is lower than the energy of products, or we say the enthalpy of reactants is lower than the enthalpy of products. You can see that the energy is going up, increasing, therefore the delta H is positive. And because delta H is positive, arrow up indicates it is a positive value. Okay, so try to avoid drawing the double-headed arrow if you're used to it in O level. Okay. Okay, so what else do I want? Okay, so transition state labeled for the exothermic and endothermic reaction. Please take note that the transition state is only temporary because it is very, very unstable. Okay, it cannot be isolated. Isolated means you cannot keep it or take it away. All right, it stays in the reaction and then it will get destroyed in the reaction as well. And the energy is much, much higher than the reactants and the products for both reactions. This is the main reason why it is very unstable. So something that is of high energy is very unstable. Okay, the symbol for activation energy is written down as EA. Okay, so that's the activation energy symbol. Okay, moving on to the next slide. The learning objective for this is in your notes. Okay, so learning objective 5.1.3, that is to define and use the terms standard condition. This syllabus assumes that there are 298 Kelvin and 101 kilopascal shown by the symbol. Okay, right. So when we talk about enthalpy change, when we talk about these values, we need to have a standard condition because enthalpy changes, the value of enthalpy changes are affected by temperature and pressure. When you change the temperature, the values will change. Likewise with your pressure. So if you want to have a fair comparison, okay, you need to use the same conditions. Otherwise, you will get a different enthalpy values when you carry out the reaction at different time and different place. Okay, so standard condition is this symbol called plimsoll. The way you draw it is just like a circle with a horizontal line across. So the symbol means that the reaction is under standard conditions. Okay, so the reason for this standard conditions is that so you can get a consistent result. Otherwise, temperature and pressure would affect your value. So what are these standard conditions? There are a few things here. Okay, so Firstly, the pressure has to be atmospheric pressure, and that's 101 kilopascal, or sometimes 1 atmosphere, 1 atm. The temperature has to be room temperature, but in Kelvin. Usually we write them down in Kelvin. 298 Kelvin is equivalent to 25 degrees Celsius. Okay. The next one, well, I'll talk about the concentration first. If we're using solutions, the concentration must be 1 mole per dm cube. It's quite standard. Okay, 1 mole per dm cube. Point number 3, the reactants and products must be in normal physical states, solid, liquid, or gas at room temperature. Okay, so what this means is that the elements or the compounds must be in their standard state at room temperature. For example, carbon dioxide, CO2, at room temperature at 298 Kelvin, it is a gas. So in order to use the standard condition, we need to use carbon dioxide gas, not carbon dioxide liquid or not carbon dioxide solid. Okay. Likewise, for H2O, at room temperature, it is a liquid. So if we want to carry out a reaction to determine the enthalpy change of involving H2O, we need to use H2O liquid, not solid, not gas. Okay, so we need to use them in their standard state at room temperature. Okay, so I've already highlighted that. Okay. So here's some additional information, which if you don't already know this, you can copy this down and just add a sticky note onto your notes. Okay, if you know this already, then that's fine, right? If we're talking about elements, okay, in the periodic table, you sort of know who your gaseous elements are. Okay, so there are 11 elements that are gases in their standard state. Obviously, your group 18 or group 0 noble gases, they're all gases at room temperature and pressure. For your halogens, group 17, we know that fluorine and chlorine are gases. Bromine is a liquid, iodine is a solid. Okay, and then your other diatomic molecules, hydrogen is a gas, oxygen is a gas, and as well as nitrogen. Okay, the liquid molecules in the liquid elements in your periodic table, as I mentioned just now, was bromine, and the other one is mercury. Okay, notice that when I talk about these diatomic molecules, they exist as 2 atoms. Okay, so be careful when you write down bromine as an element. Okay, don't write it as Br or Cl. Don't write it as Cl. They always exist as a diatomic. So please write down the correct symbol. Okay, and then everything else in your periodic table, these elements are solid at room temperature. Okay, so for the elements, it's easier. What about compounds? How do you know if a compound is a solid state or a gas state? Okay, so there is no there is a long continuous list of compounds with their standard state at room temperature. Okay, so the only way for you to learn is as you go along. Okay, so this being said is if you see that molecules all the time, then you would already know what state it is in at room temperature. Okay, so I don't expect you to memorize a whole list because there's a lot of possible compounds out there, but the pretty obvious ones are the ones that you meet all the time, like carbon dioxide, you know that it's a gas. Ammonia, you also know that it's a gas at room temperature. Okay, so those are some of the examples that I can give you. Okay, moving on. Now we move on to the specific enthalpy change. Okay, so you will look at enthalpy change of reaction. Well, that's quite general. Okay, enthalpy change of formation, where you see the symbol as delta HF, combustion, delta HC, and neutralization, delta H neut. So these are the enthalpy changes that you need in AS level. So there will be more in A2 level. If you see other enthalpy changes like enthalpy change of atomization or enthalpy change of hydration or enthalpy change of solution, these are the ones that will be covered in A2 syllabus later on. Okay, standard enthalpy change of reaction. So this is the enthalpy change of any reaction. It's very general. Okay, so the definition is when amounts of reactants in the stoichiometric equation react together under standard conditions to give products in their standard states. So basically, this is just putting the standard conditions into definition, okay? Because there is the logo, the standard logo there, or what we call the Plimsoll logo. That means the reactions have to be carried out under standard conditions. Okay, so that's why standard states is mentioned. Stoichiometric equation, I will show you in the example shortly. Okay, where it mentions stoichiometric equation, this is your mole ratio. Okay, so your enthalpy change value depends on your mole ratio. So first example we have here is a reaction between hydrogen and oxygen to form water. Okay, so that means the enthalpy change or the energy given out, because it's negative, the energy given out when hydrogen reacts with oxygen to get 2 moles of water is negative 572 kilojoules per mole. Okay, then the question asks, what about if I want to form 1 mole of H2O? Okay, so I know the value for when I form 2 moles. What is the enthalpy change when I form 1 mole of H2O? Now I notice there's a typo here. That should be half O2, okay, not 12. I think in your notes it is correct. Yeah, so I'll just change this. So that becomes 1/2. Okay, so since the value to produce 2 moles of water is negative 572, the enthalpy change to form 1 mole of H2O would be just half of that number. Okay, and it turns out to be negative 286 kilojoules per mole. So this is what we meant by enthalpy change depends on the stoichiometric ratio. Okay, so if I just give an explanation here, this is the enthalpy change when 1 mole of H2O is produced. Whereas this is the enthalpy change when 2 mole of H2O is produced. Okay, and actually this reaction, the second one, is a reaction for the delta HF of H2O liquid. So this is the equation for the enthalpy change of formation of water, and this is also the equation for delta HC, combustion of H2 gas. Okay, so I will cover enthalpy change of formation and enthalpy change of combustion after this. So you can see that formation is referring to H2O because I'm forming H2O. Combustion is referring to hydrogen because I'm burning hydrogen in oxygen, right? So if you want to copy this down, another thing that I want to add on before you copy this down, enthalpy change of reaction, the value can be positive or negative. Okay, so if you want to copy this down, you can pause here. Okay, next enthalpy change that we're going to look at is the enthalpy change of formation. So the symbol is delta HF, where F stands for formation and the Plimsoll symbol stands for standard condition. Okay. By definition, it is the enthalpy change when 1 mole of a compound is formed. This is important. 1 mole of a compound is formed from its elements under standard conditions. Okay, so under standard conditions, you don't have to memorize that. If you see the symbol, you just automatically that is the standard condition symbol. Okay, both compounds and elements are in their standard states. So that means they're the standard state at room temperature, right? So what do I mean by this? Let's have a look at the equation, right? So this example requires us to write down an equation for the enthalpy change of formation of silver chloride. Okay, so I always have to refer to the definition if I want to write down the equation. Okay, so my definition says that I am forming 1 mole of compound. Okay, so that means I form 1 mole of silver chloride. So you have to get the formula correct, because if your formula is wrong, then your mole ratio, your equation will be wrong, and then later on your calculation will be wrong as well. Okay, so that's my 1 mole of silver chloride. This have to stay fixed. It has to be 1 mole. I know usually I don't write down number 1 if it's just 1 mole, okay, but this is important because I have to strictly follow the definition. Okay, so it is the enthalpy change of formation from its elements. Okay, so the elements that I have in silver chloride is, of course, silver and chlorine. Okay, now remember, both compounds and elements are in their standard states. Chlorine exists as a diatomic molecule, so it has to be Cl2. Chlorine exists as diatomic molecule. You cannot just write down Cl. Okay, that is an atom, not, well, it doesn't show you the standard state of chlorine at room temperature, because chlorine exists as a Cl2. Chlorine doesn't exist as a Cl atom. Okay, whereas silver, it exists as a giant metallic structure, and silver would be solid. The formula of silver is also just Ag. Okay, so the standard state is a solid because we know that silver is a metal. Chlorine, we know that chlorine is a gas. Silver chloride, this is where it can be tricky for you Okay, you may think aqueous silver chloride. Now remember, silver chloride in your qualitative analysis notes, silver chloride exists as a white precipitate. Okay, so the state symbol of silver chloride is solid. All right, next, so I've got my formula correct. My elements are in their standard state. My state symbols are done. The last thing that I should check is to balance the equation. Okay, now I cannot change the number here because by definition, silver chloride must be 1 mole. So I can only change the number of silver or the number of chlorine. So in this case, I've got 1 silver. I only need 1 chlorine, so I make it half. And that represents the enthalpy change of formation of silver chloride. And the value is somehow missing. Usually we should write it as enthalpy change of formation. We are talking about forming silver chloride, and 1 mole of silver chloride. We write it as delta HF AgCl solid to be negative 127 kilojoules per mole. Okay. Next is the enthalpy change of formation of solid. Okay, so now we've got a hint given. Potassium manganate. Okay, so I want to know the enthalpy change of potassium manganate. So strictly speaking, they should write it as delta HF KMnO4 as negative 813. Okay, right, back to my equation. I want to form potassium manganate, which is a solid. Okay, maybe I'll change. Sorry. KMnO4 solid as given in the question. And because it is enthalpy change of formation, my compound, my product has to be 1 mole. So I have to keep KMnO4 as 1 mole, right? It is formed from its elements in their standard state. So first I need to list down. I know that there's potassium. I also know that there's manganese. And I also know that there's oxygen. Now be careful with oxygen. It exists as diatomic molecule. So I have to write down O2, right? Next is the standard state. Potassium is a group 1 metal, solid. Manganese is a transition metal, solid. Oxygen is a gas. Lastly, I need to balance the equation. I cannot change KMnO4, that stays as 1. K is 1, Mn is 1, and there are 4 oxygen on the product side. So that means on the reactant side, I need to make my O2 as 2 moles. Okay. Okay, so if you want to pause the video, you can pause it here. Okay. Next is the third question, the third example. They want us to write down the enthalpy formation of O2 gas, and they want us to write down the value of the formation of O2 gas or formation of element. Okay, so I want to form 1 mole of oxygen gas, okay, from its elements. Oxygen as an element is O2, and it is also a gas, okay? So this is the enthalpy change of formation of oxygen gas. And you notice that going from the reactants to products, there isn't really any changes there. There's no reaction, okay? So the enthalpy change of any, the enthalpy change of formation of any element would be 0, okay? Because there's simply no change. Or we can say there's no reaction really. So if there's no reaction, then there isn't really a change in energy or change in heat, okay? So the reason why the enthalpy change of formation value is 0 is because element forms, oh, okay, never mind. Actually, I will just omit this because I already mentioned that there's no change, there's no reaction, okay? Next is the enthalpy change of combustion. So the enthalpy change of combustion is always negative. Forgot to mention that the enthalpy change of formation can be positive or negative. Okay, that means it can be exo, it can be endo. Whereas combustion, when you burn something, when you heat something, it will always release energy. When you combust or when you heat something, always release energy. So it's always only negative. Okay, here, negative only. Definition of enthalpy change of combustion is when 1 mole of a substance or 1 mole of a compound is burnt completely with oxygen under standard conditions. So anything that reacts with oxygen in 1 mole is considered combustion. Okay. Again, under standard conditions, because you see the Plimsoll symbol. That is the symbol for standard condition. Okay. So enthalpy change of combustion is different from enthalpy change of formation because for formation, we make the product to be 1 mole. Whereas for combustion, we need the reactant that reacts with oxygen to be 1 mole. Okay, so it's not the oxygen that is 1 mole, it's not the product that is 1 mole, it is the reagent that burns with oxygen to be 1 mole. Okay, so what do I mean by this? I'll show you in the examples. So you are expected to write down the enthalpy change of combustion of ethene. That means we are burning ethene, and ethene has to be 1 mole. Okay, so ethene is C2H4 and it is a gas. Okay, usually your alkanes and alkenes up to carbon 4, they are most likely to be in gas state, right? So combustion, again, it reacts with oxygen. You need O2 gas. So this has to stay fixed. That's why I draw it in a box. What are the products of combustion? We know that you will produce CO2 and H2O. Okay, CO2 is a gas and H2O at room temperature is a liquid. Next thing to do is to just balance it. Okay, so it turns out that you need 3 oxygen, 2 carbon dioxide, and 2 H2O. When you write down the enthalpy change symbol, you should be writing down the substance burnt. Okay, so it's the enthalpy change of the combustion of C2H4 is negative 1,411 kilojoules per mole, or Another way of saying this is that ethene gives out 1,411 kilojoules per mole of energy when 1 mole of it is burnt with oxygen. Okay, so if you use 2 moles of ethene, then you just multiply it by 2. But by definition, delta Hc is 1 mole of ethene. Okay, the enthalpy change of combustion of sulfur to form sulfur dioxide. So we are burning sulfur. So sulfur has to be 1, and sulfur is a solid. We burn in oxygen to form an SO2 gas. Oxygen is a gas, and you can see that the negative sign, this is because whenever you burn something with oxygen, you will release energy, you will give out energy, you will give out heat. Okay, so it is an exothermic reaction. Okay, now if you notice what I just wrote for the combustion of sulfur, this also represents another enthalpy change. It also represents enthalpy change of formation of SO2 gas. Let's check. By definition, we form 1 mole of SO2 in its standard state from elements in its standard state. So it complies with the definition of enthalpy change of formation. Okay, so it's the same. Delta Hc of sulfur is the same as delta Hf of SO2. And the values are also the same because the change is the same, the equation is the same. Okay. Next. Third question. Which one is the enthalpy change of combustion of hydrogen? So enthalpy change of combustion of hydrogen means we are burning hydrogen. So the correct symbol for this is delta Hc of H2 gas. When we burn hydrogen, hydrogen needs to be 1 mole. 1 mole of a substance that burns. Okay, so I hope you can easily spot B as the correct answer because enthalpy change of combustion is referring to 1 mole of hydrogen burnt with oxygen. Okay, here you've got 2 moles of hydrogen, here you've got 1 mole. So this is the correct one, 1 mole of hydrogen. Notice that the numbers are doubled. So this agrees with the fact that if we double the number of moles, the enthalpy change also doubles. Okay, so you can check that 286 is half of 572, right? Now, sorry, that should be half, not 12. Okay, and I've mentioned this earlier already. Apart from calling this equation or reaction the enthalpy change of combustion of hydrogen, this is also the enthalpy change of formation, delta Hf of H2O. So be careful when writing down the label, right? Here, it has to follow the enthalpy change. If you're talking about combustion, it's the reactant. If you're talking about formation, it's the product, all right? But they both are the same, so they give the same value, -286, right? Okay, next. So we are now going to calculate the enthalpy changes from appropriate experimental results, including the use of the relationships Q equals to MC delta T and delta H is equals to negative MC delta T over N. Okay, so you have done the practical for enthalpy changes actually. Okay, the one that involves change in temperature, those are your experiments to determine the value of enthalpy change experimentally. Okay, right. So enthalpies of combustion can be calculated by using calorimetry. So calorimetry is a technique used to measure changes in enthalpy of chemical reactions. So a calorimeter can be as simple as using the polystyrene cup. Remember where you support it in a test tube and then you fill it in water or solution. You take the temperature of the solution before and after the reaction. So this reaction, this experiment is actually a calorimetry. Okay, you can use a vacuum flask as well or a metal can, but we don't use this in school lab. Combustion is easy. It's a relatively easy experiment to carry out in the lab because you just burn a fuel. Okay, so fuel can be anything, the substance that you are burning. Okay, so that's what fuel is. We burn fuel to give out energy. And as I've mentioned earlier on, combustion is always exothermic. So regardless of what you burn, whether it is labeled as fuel or not, burning any substance will give out energy. So automatically it becomes a fuel. All right. So the fuel is burnt and the flame is used to heat up water in a metal cup. Okay, so I'll explain to you what happens here. So this is a typical apparatus setup used in a simple laboratory, in a simple lab, if you want to measure the enthalpy change of combustion of ethanol, for example. Okay, so burning of ethanol and combustion of ethanol, they're the same thing, right? So I'll talk about the setup first. Usually you will have a burner here. So this is where your combustion reaction is happening, right? So combustion happening here. Okay, and then usually, since combustion give out heat, we cannot measure the heat directly from the flame. Okay, it is one, not accurate. Secondly, it's also not safe because you do not want to bring a thermometer to a direct to the flame directly, right? And if you do it at a distance, then you're not really measuring the heat energy of the combustion reaction. You're just taking the temperature of the air. Okay, so what happens is that we can place a beaker of water near the combustion reaction so that whatever heat is given out here in the combustion process will be transferred to the water. So the energy given out will heat up the water, and this energy can be measured using a thermometer. All right. Now you may argue, but what if my combustion heat is not directly transferred to the water? So this is where heat loss is coming in. All right. So I would imagine the one that is the heat transferred would be the one that's closest to the beaker of water, right? And you will have some heat transferred to the site, to the environment, to the string, to the burner, everything else. Okay, that's why we acknowledge there is some heat loss. We acknowledge that not all the heat from combustion will be transferred to the water, but we try our best. Okay, so we make do with what we have. That's why in a experiment that involves heat, the values will be very, very different or very far off from the literature value. Okay, literature value is like the data or the value in a system or in a library, right? Okay, so let's go through this details here. The thermometer is there to record the temperature of water before and after combustion of ethanol. Okay, so you want to know how much the temperature have changed after the combustion happened. Okay, so in order to do this, you need initial and final. Okay, so that's why you have before and after. As for the calorimeter or the cup that we use, in our lab, we use the polystyrene cup. Usually the best one is to use copper, but we don't have that, or at least we don't have a lot. Okay, so we just choose the most suitable material, the material that minimizes heat loss. Okay, and polystyrene is good enough. This is what I was explaining just now. Combustion of fuel, in this case, it's ethanol. So when we combust ethanol, energy is given out and that energy will be transferred to water. That energy is the one that will heat up the water in this beaker. Okay. So water will absorb as much as it can. Okay, we acknowledge that it's impossible to get all the heat from the combustion, but water will absorb as much as it can. The energy released from the burner due to combustion. So energy absorbed by water can be calculated using this formula. Q is equals to mc delta T. I'll go through these terms in the next slide. Okay, so we say that energy released by burning of ethanol or burning of whatever fuel is equals to the energy of absorbed by the water. So if we can find the energy here in the water, it's easy to do because we can find the temperature before and after. Then the energy is also the same from here in the burner. Okay, right. Okay, so I hope that is clear. Next, we're going to talk about this expression. This expression is the one that is used to find the energy in the water that was given out by the burner. Okay. Right, heat transferred. So Q is the heat transferred, right? So we cannot possibly do any measurement here because it involves burning, open flame. So we do not want to put a thermometer near it. Okay, so we can only do the calculation from the beaker of water. At least that's safer. We can put a thermometer inside that water. Okay, so that's Q, heat transferred, is equals to, heat transferred, sometimes called enthalpy change. The unit is in joules. Okay, so Q is in joules. M is the mass of water. Okay, so the mass of substance that we are measuring the temperature of. So mass is usually in grams. Okay, mass that we're talking about, well, there are two masses here, so be careful. There's mass of water. There's also mass of the alcohol. The reason why we want to know the mass of alcohol is because we want to know how much we have burned. Okay, we cannot just simply, or just put whatever value and then we can find enthalpy change. No, it depends on how much ethanol is burnt, the number of moles of ethanol burnt, and its respective energy. The more ethanol you burn, the higher the energy, of course. Okay, so the mass is referring to the water, right? So I'll talk about the mass of ethanol later on. C is the specific heat capacity of water. C is just like a constant. So don't have to worry about C. It's a constant that has a value of 4.18. The units of C is joules per gram per Kelvin. Okay, so that's missing. So by definition, specific heat capacity of a substance is the amount of energy needed to change the temperature of 1 grams of the substance by 1 K. Okay, so joules per gram per Kelvin. But sometimes, oh, I think I know why. It doesn't have a, sorry about that. It doesn't have a unit, okay? Because the next one, delta T, is the change in temperature, okay? The change in temperature is referring to the temperature of water because that's where our thermometer is. I know we are interested in the combustion of ethanol, but we cannot do direct measurement on this ethanol. So we can only rely on the water, right? So delta T is change in temperature. So this is final minus initial. It depends whether it's a temperature rise or temperature temperature rise, temperature drop. Okay, so whether the temperature is going up or the temperature is going down, it follows the same formula still, final minus initial. Okay, delta T doesn't have unit because it's just a change in temperature. Okay, so I have just confirmed that there is a missing Kelvin here. Grams to the power of -1, Kelvin to the power of -1. Okay, so I'll just, that is for specific heat capacity, which has a value of 4.18 joules per gram per Kelvin. Okay, so please make sure you add this to your notes. So that means delta T, change in temperature, is in Kelvin times by Kelvin. Okay, if you know how to work this out, the units of MC delta T, the units of M is grams, the units of C is joules per gram per Kelvin, and the units of delta T is Kelvin. So you can see that the Kelvin cancel out nicely. The grams cancel out nicely. So that gives you the unit for Q, heat transferred or energy, as joules. Okay, so you can see that because the unit is in joules, that means we're talking about energy, right? So please make sure you correct the missing Kelvin to the power of -1 in your notes, okay? So it's Kelvin to the power of -1. Okay, another thing that I want to point out is the temperature change, even though it says it is in Kelvin, but I want you to know that temperature change in degrees Celsius is the same as in Kelvin, okay? It's the temperature change, not the temperature alone. I will show you in example later on how come temperature change in degrees Celsius and Kelvin is the same, okay? In terms of mass, sorry, I'm jumping all over the places now. Mass of substance, okay, usually the water is given in volume, like 100 centimeter cube, okay? But we will assume, so at this, we usually assume 1 centimeter cube to be equals to 1 grams for any solution unless stated otherwise. So we're taking the density to be 1 grams per centimeter cube. Okay, so we just convert the volume to grams, right? As in a 1-to-1 ratio. Okay, let me just check if there's anything that I want to add on here. That should be everything. Okay. Next is delta H. Now, delta H is related to Q, small q, the heat, the energy transferred or the heat transferred, okay? Delta H is equals to MC delta T. Now, does this look familiar? MC delta T is your Q. So that means delta H is equals to Q over N. So once you know your Q, you just divide it by N, where N is the number of mole used in the experiment to react. Okay, now this is where it gets confusing for the students sometimes, right? Number of moles. Are we talking about the number of moles of the water or the number of moles of the ethanol? Okay, since this is combustion, for example, we want to know how much mole of the ethanol is being combusted. So we go back to the definition, all right? Enthalpy change is for combustion. That means we are burning ethanol. So the number of moles that we're interested in is of ethanol. Okay, so for example, in this case, for combustion, delta HC is of ethanol. Therefore, we're interested in using the number of mole of ethanol. Okay, so N depends on the experiment. It can be combustion, in which case it's the number of moles of substance burned if it's combustion. It can also be number of moles of acid or alkali used in the case of neutralization. It can also be number of moles of solid dissolved in the case of solution. All right, so it's a case by case scenario. Another thing that's missing from this is delta H is the enthalpy change per mole, and the units is in kilojoules per mole. Okay, so remember that means your Q has to be in kilojoules. Previously, our Q is in joules, so that means you need to convert over moles. So that's how you get the units for enthalpy change. Okay. Now we're going to do one question before we end this lesson. Example 4. Okay, so let's have a read. Example 4. Calculate the enthalpy change of combustion for the reaction where 0.65 grams of propanol was completely combusted. Okay, so let's highlight. You want to find the enthalpy change of combustion. That means we are interested in delta HC of propan 1-ol. So that's your CH3, CH2, CH2OH. Okay. And then it is used to heat up 150 grams of water from 20.1 to 20.1 degrees Celsius to 45.5 degrees Celsius. Okay. Right. So you don't have the diagram here, but I do have the diagram. I show you the diagram, but in the exam, you wouldn't have the diagram. Okay. So this water is 150 grams. And then in the combustion burner, we have 0.65 grams. So please make sure you are able to distinguish between these two masses. Okay, because if you use the wrong mass for the calculation, then your answer will be wrong. Okay, so I want to show you delta T. All right, so delta T is the change in temperature. So delta T is taken as final minus initial. Okay, and that turns out to be 25.4 degrees Celsius. All right, now I'm going to show you that it is the same in Kelvin as well. So how do you do this is you should not convert 25.4 degrees Celsius into Kelvin. That's wrong. You should convert each initial and final temperature to Kelvin. In this case, it's 293.1, maybe different color. 293.1 Kelvin. And the final temperature is 318.5 Kelvin. So if you take that and find the change in temperature, you should get 25.4. Okay, so that shows you that it's the same, whether it's degrees Celsius or Kelvin, you just change the unit. right? First step in question, sometimes they tell you the first step, sometimes they don't. Okay, so delta T, sorry, sometimes they just ask you to find straight away the enthalpy change without giving you the steps, right? But in your notes, I have provided you the steps so that you can use the same steps for when you do questions later on. Okay, so delta T 25.4 is of the water, okay? Not here. So read the question carefully. Used to heat up 150 grams of water from 20.1 to 45.5. Okay, calculate the energy change used to heat up the water. So first, I want to find the energy. Q is equals to mc delta T. Mass would be mass of water, because that's where my delta T is, right? Mass of water is 150 grams, nice. Times by C is my specific heat capacity, which is a constant. So I like to put in my units so I don't get it wrong. Times by delta T, which is 25.4. Since T is in Kelvin, and since it's the same as degrees Celsius anyway, so I can just write it as Kelvin. And I can conveniently cancel out my units, okay, to give me an answer of 15925.8 joules. Okay, my final answer to three significant figures would be 15900 joules. Three significant figures. Always remember this. Okay. So please take note that the mass here is of the water and not of the alcohol. Okay, next. Calculate the number of moles of alcohol combusted. Okay, so that's quite clear in the steps. Number of moles of propanol is equals to mass over mR. Mass of propanol is given as 0.65 grams. And the mR of propanol is 60 grams per mole. Yeah. Okay, so again, that cancels out. You bring up the mole minus 1, it becomes mole. And the answer for this is 0.0108 mole to three significant figures. Please check the calculation for me just in case I made a mistake in my calculation, which I usually do. Okay, right. So I already know from step 1 the energy that was transferred to my water, and that energy 15,900 joules is correspond to 0 when I burned 0.0108 mole of ethanol. Okay, next step is I want to know the enthalpy change, and enthalpy change is per 1 mole of substance burned. That means per 1 mole of propan 1 all burnt. There are two ways of doing this, okay? But first things first is converting Q from joules to kilojoules. In this case, I divide it by 1000 to get 15.9 kilojoules. Okay, so method A and method B. Method A is by using the expression delta H is equals to Q over N, where N is the number of moles of ethanol. So that means I take the energy that was released by the number of moles of ethanol that was burned. Okay, so 15.9 kilojoules divided by 0.0108 mole to give me 1472.2 kilojoules per mole. Okay, so you can see my units there. Nicely done. Second way of seeing this is that when I burn 0.0108 mole of propanol, I get 15.9 kilojoules of energy. What is the amount of energy released since it's combustion when I burn 1 mole of propanol? And this is actually just the same. 15.9 divided by 0.0108. So it's up to you whether you want to choose method A or method B. Okay. Lastly, final answer is delta H, enthalpy change of combustion of propan-1-ol. You can use the formula, okay, structural formula, no problem. CH3, CH2, CH2OH is equals to, I need the answer to be in 3 significant figures, so 1470 kilojoules per mole. Don't forget 3 significant figures done. Units done, kilojoules per mole, and it's in the correct unit. The sign is important. If my temperature increases, that means it is an exothermic reaction. And it turns out that my delta T increases. So it is an exothermic reaction. And as we all know, all combustion reactions are exothermic reactions. So you need to include the negative sign. So my final answer is negative 1470 kilojoules per mole, and that's in 3 significant figures. Okay, so if you're wondering what that sign is, I am referring to that negative charge. So please make sure you understand the steps and the process here. Okay, so if you want to work this out, please make sure you check the calculations are correct and you understand the steps. If you don't understand it, please let me know. But I will do 2 more examples, I think, when it comes to calculating enthalpy change experimentally. Okay, so let me just, okay, so that's example 5. I will not go to example 5. I will stop here for now. Don't forget to fill in the questions in forms. Okay, the link can be found in the description box of this video. All right. Thank you so much for your attention. I know there's a lot of things that we covered, but the only way to check whether you have understood this topic or not is only by doing questions by doing the calculations. Okay. All right. Assalamu alaikum and thank you, everyone.